Okay, welcome. We're looking at SAT Worksheet 212, Statistics, and let's talk about exactly what this worksheet entails and what you'll need to know for the test. So as far as statistics go, there are two big kind of buckets that I would group the test into. One is the familiar. The familiar is, I'm sure you've had practice with getting the mean or average, the median, the mode, and the range. If you forget what one means, not a big deal. Each one is defined in this worksheet. So that's half of what you need to know for statistics on this test is the familiar. The other half is something that you may not have seen for GCSE. Standard deviation, margin of error. Most people are not familiar with margin of error. It's simple enough concept once explained. And box and whiskers plots, which are coming up more and more frequently on the test. So I would call these, for most people, the unfamiliar. So interestingly, what the test does is it manages to make the familiar unfamiliar sometimes if you're not used to how they ask problems and how they present data. And the unfamiliar is something that is easy enough once it becomes familiar. So with no further ado, let's kind of look at the familiar first and see what it looks like on the test. So I'll present a couple examples, then we'll try a few practice problems. Okay. So let's look at this example first. And if you want, you can take a moment to try to solve it yourself. It's this one right here in red. So we have Linda wants an average of 85 in her biology class. Her current average is an 82 after 4 tests, and all tests are weighted equally. What must she score on her 5th and final test in order to achieve her goal? So the familiar is we know how to calculate an average, right? It's just the sum of everything divided by the number of terms. Like if I wanted to know average points per game, I would add up all the points and I would divide by the number of games, and that would get me my points per game, my average points per game. So it's usually total of whatever comes before the per divided by total of whatever comes after the per. So if I wanted average points per game, it would be points per game, and all points would be in the top. Total number of games would be in the bottom. Well, on this one, and I'll even write that, total points, total games. Okay. Well, what I find is helpful is to usually just create this average skeleton. So they'll tend to give you bits and pieces, but they don't usually give you all the points and all the number of games so that it's straightforward. They usually give you other pieces and you have to figure out what you're missing. So it's helpful to always kind of fill in what you know amongst this average equals sum of terms over number of terms. In other words, all points over total number of games. Fill in what you know and then find out what you don't know. So her average in biology is an 85. Or she wants an 85, really. Her current average is an 82 after 4 tests. So here's what we know. We know that she wants an 85 after 5 tests, which is going to be the sum of the 4 tests plus the 5th test divided by the number of tests. So here's what we do have. We have that there will be 5 tests, and we have that the sum of the first 4 So the sum of the first 4 tests plus the 5th will get us the average. We'll call the 5th one X. So here's something else we can fill out. If her current average after 4 tests is an 82, that's 82 equals the sum of every test she's taken, so adding up all the points, divided by the total number of tests, which is 4. So we can figure out the sum of those first 4 tests, just 4 times 82. So I think we're looking at 328 here, because 4 times 8 is 32, 4 times 80 is 320, and then add another 8, so 328 is the sum. So then what we would do is we'd plug in what we know and we'd figure out what we don't. So we know that 328 plus X divided by 5 has to average 85. So now we'll just isolate X, right? It becomes any type of average problem we've ever done before. And because we're tight on space, I've actually done the steps here. So we have 328 plus x, the fifth test, divided by 5 equals the average. Multiplied by 5, we get 425 equals 328 plus x. Subtract 328, and we know that she has to get a 97 on her last test. So again, my best advice for any average problem is fill in what you do know within this average framework or skeleton and use it to figure out what you don't. So let's look at another one. This is another Linda problem, but we've stepped it up a notch. And feel free to pause and try it on your own if you want to. But what it says is Linda also wants an average of 85 in her literature class. Ironically, her current average is an 82 after 4 tests in that class as well. However, the final test counts for double the amount of the 4 prior tests. So that's where things get a little tricky. What must Linda score on the 5th and final test in order to achieve her goal? So again, what we want is we want an 85. And what we do know is we know that she has an 82 after her first 4 tests. So that's sum divided by 4, sum of all the terms. And we know that's a 328 again. So she has a 328 is the total number of points she has on her first 4 tests. Here's where things get tricky. Her 5th test counts as double. What does that mean? That means that we're going to add the 5th test twice. And instead of dividing by 5 terms, we have our first 4 terms right there. And then the 5th test twice. So we're going to divide by 6. Okay. Why don't we, so some people may ask, well, why don't we just double it and divide by 5? Well, if you were to double it and divide by 5, think of it this way. If you were to take one test and it were to count for double, so say the test counted for 98, you do 98 plus 98 divided by 2, and that would get you an average of 98. Well, if you don't put a 2 in the bottom, if you just put a 1 in the bottom, 98 plus 98 divided by 1, you're going to get an average way over 100%, right? You're going to get an average of 196. So that's why in here, if it counts as double, you have to write it out twice and count it twice in the denominator as well. Anyway, what happens here is we have 6 times 85 again, and I'll scroll down. So that gives us 328, and we're looking at, 6 times 85 gives us 510, and we have 510 equals 328 plus 2f, because two of the 5th tests. And then subtract 328, right? So we get 182 equals 2f. So in this case, f is going to have to be 91. So if something is weighted as extra, you count it as however many extra on the top, but you also have to make sure it represents that number of terms in the bottom. In this case, double means 2 on the top, 2 on the bottom. Okay. So that's kind of averages, and we'll look at an average problem from the test in a moment, but let's look at a histogram here that tests us on median. So it says the histogram above shows the distribution of heights in meters of 26 pyramids in Egypt. Which of the following could be the median height of the 26 pyramids represented in the histogram? Okay, so the first thing to understand is how a frequency chart or a histogram works. And the way it works is this. We're going to have 2 scores that are going to be between 15 and 30. So you could almost write that out twice. We're going to have 3 scores that are going to be between 30 and 45. But as you're noticing, it would take a while to write out all of our scores in order to figure out the median. We could write them out in order, and then we could cross off, because there are 26 pyramids, we know that scores 13 and 14 are going to represent the median, right? So we're going to have to cross off the first 12 scores, the lowest 12 scores, and then we hit the 13th score, and the 13th and the 14th score averaged together will get us our median, right? I mean, you can think about it this way. If I had like 2, 7, 8, 9, 11, 12. Well, if we have 1, 2, 3, 4, 5, 6 numbers, what would we do? We'd cross off the first two, and then we would take the third and the fourth. And the average of those, 8.5, would be our median. That's if you have an even number of numbers in the data set. So with this frequency chart, we're essentially just going to do the same thing. Instead of writing everything out, we know that we have 2 of these if we write them out, right? We know we have 3 of these. We know we have 12 of these. And because we're looking at 26 in total, we're just trying to get in 13 from the bottom. So this gets us away 5 from the bottom, right? So then we need to get another 7 from the bottom to get to the 13th. So we cross off 7 of these, which leaves us 5 of these. So our 13th and our 14th term are going to be between 45 and 60, which means that our median is going to be between 45 and 60. So it says, which of the following could the median height of the 26 pyramids be? It could be 48 meters. Okay. Let's take a quick look at this example too. So this example involves both the median and the mean. So it says, the histogram above shows a distribution of the number of books read by 25 college students during 1 week. Which of the following is true for this group of 25 students? Okay, so to get the average, what do we need? We need total books over total number of students. That will get us the average books per student, right? So it's total books over total students. Simple enough. So how do we set this up? Well, I'll show you exactly how we'd set it up. Right here we have total books over total students. What we'll do is we have 5 students with 0 books. So 5 times 0 adds 0 to our total number of books. We have 9 students with 1 book. So that adds 9 books. 4 students with 2 books. So that adds 8 books. 1 student with 3 books. 2 students with 4, 2 with 5, and 2 with 6. So that's going to add another 8 books, 10 books, and 12 books. We add these together, we get our total number of books, divide by 25, and we get that the mean is 2. So we need to figure out what the median is as well, because all of these answer choices are asking us about the mean, median, and mode, and the range. So let's figure out what the median is, and then we'll also, so first off, we know the mean is 2. Okay, so our median is going to be, we have a total of 25 students. So our median is going to be what student 13 said, right? So we want to go 12 from the bottom, right? If we listed these out, we would have 5 zeros, 1, 2, 3, 4, 5. We would have 9 ones, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'd continue listing out, but because we'd have 25 numbers, we'd want to go 12 from the bottom, right? So in order to get right smack dab in the middle, the median on an odd number of numbers. So we have a 5 here. We have a 9 here. We cross off 5, and if you think about it, to get to 12, we still need to cross off another 7. So we cross off another 7, and we're left with 2 here. And you can see this illustrated here at the top too, but it's faster to just kind of do it without having to write it all out. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we know that number 13, the smack dab in the middle, is going to be a 1. So we know our median is 2. We know our median is 1. Our mode is just the most frequent. When you think mode, think most. So the mode is going to be 1 as well, right? Because 9 is the most frequent. 1 comes up the most often with a frequency of 9. And then our range is 6. We go from 0 to 6 books. Okay, so let's take a look at the statements. And I'll zoom out so we have all of our data in front of us. Okay, zoom out just a little bit more. It's a little bit of an eye test. Okay, so the mean, the average number of books read is equal to the median number of books read. Well, we calculated the mean, we calculated the median, and that's not true. So anything with 1 goes. So actually, it has to be C. All you have to do is figure out 1, and you know it's going to be C, because all the other ones include 1. But just to be safe, the mode number of books read is equal to the median. Well, yes, they're both 1. The range of the number of books is 6. Well, that is true as well. So it is 2 and 3. Okay. Let's just try a few problems from the test. One of the problems that I've marked is probably the hardest one on the first half of concepts, the familiar concepts that gets everyone. So I think we'll do 2 problems. We'll do one that I think is just a good mix of several different skills, and then we'll do the hard one that tends to mess people up. I'm going to skip 20 because it's similar enough to what we just did. Okay, let's do 24. So this concept is a really cool concept. If you want, you can pause it and try it yourself. As always, I'm just going to keep on going. So it says, of 100 people who played a certain video game, 85 scored more than 0, but less than 10,000. So out of 100 people, 85, the vast majority, are going to be between 0 and 10,000. 14 people are going to be between 10,000 and 100,000. So 14 people, 10,000 and 100,000. So a small fraction of the people out of 100 scored within this range. And then we have one person who's a major outlier. One person scored 5,350,000 points. And that's just one person. Okay. Which of the following statements about the mean and median of the scores is true? So this is a phenomenon. I'm just going to tell you the answer on this one. The mean is greater than the median, but I want to explain the phenomenon because that's what's more important. And we'll look at the other answer choices in a moment. But the idea is this. If you have an outlier that's really high, what is that outlier going to do to your average? It's going to boost your average way up. Think of it this way. If I have a low-income neighborhood where the average income is about $20,000 a year, and then Bill Gates moves in who makes, let's say, $2 billion a year, what's the $2 billion going to do to the average? The average all of a sudden is going to become like $3 million, right? So one outlier can really skew the average. It can really shoot the average up if the outlier is high, or it can shoot the average down if the outlier is low. And the average actually becomes a number that doesn't really represent the data as a whole. So in the case of this outlier, we know that the median is going to be somewhere within this range, right? We crossed off 49 numbers, and our 50th and 51st number are going to be somewhere between 0 and 10,000. But this guy on the average is going to skew our average probably way higher than 10,000. So what we know is we know that the mean is going to be greater than the median. If that doesn't make sense conceptually, here's a way to try it. Take a data set where you have, let's say, 1, 3, and 5. In this one, our mean and median are the same. They're both 3. They're both 3. If you add these up, you get 9. Divide by 3, you get 3. Okay. Now, throw in another number like 100. Well, our new median is going to be 4. It's going to be halfway between 3 and 5. So our median is still fairly representative of where most of the numbers are, but our average is going to be skewed way up, right? You're looking at 109 divided by 4. So you're going to get, about 27 or so, a little over 27. So that's, yeah. Anyway, the median is greater than the mean. No, because the median is going to be within this range. The mean and median are equal. Definitely not. There's not enough information. a lot of people go for D, but there is enough information. How do we know there's enough information? When you have an outlier that's that high, that far above your median, it's going to skew things outside of this range. Okay. Here's the, not this problem actually. This problem is a major challenge problem. This problem gets a lot of people. So I'll go through it, but if you want to try it yourself, give it a go. But I'm just going to go through it. An online store receives customer satisfaction ratings between 0 and 100 inclusive, meaning including those two numbers. In the first 10 ratings the store received, the average of the ratings was 75. What is the least value the store can receive for the 11th rating and still be able to have an average of at least 85 for the first 20 ratings? So again, this is an average problem where we're juggling a lot of pieces of information. So let's just start to create the skeleton, right? Average equals total number of points, right? So sum of everything divided by number of terms. Sum of terms divided by number of terms. So let's figure out what's going on here. So what we know first is that our the first 10 ratings received an average of 75. So 75 equals the first 10, we'll call the first 10 A, divided by 10. So the sum of the first 10 is going to be 750. So that's the first 10. We're going to know what's the least value the store can receive on the 11th rating and still have an average of 85. Well, here's what we know. 85 has to equal A plus the other 9 ratings, so I'll say 9 and then R for ratings, plus X, right, the 11th rating. And we have a total of 20 ratings. Well, here's what we know here. We know that the 10 ratings is a 750, the first 10. And we're trying to figure out X, and we need to figure out a number for R for the 9 other ratings that's going to allow us to make X as low as we can possibly make it, right? Because we're going to know the least value on the 11th rating. So what we're going to do is we're going to make R 100. So that means we're going to get 900 total on those 9 ratings. Why do we make R as high as we can make it? Because it allows us to make X as small as possible, right? In order to still average out to an 85. The higher we make this, the lower we can make that. So anyway, we have 750 plus 900 plus X divided by 20. Now we know that this is 1700. And we have 1650 plus X. So if we really wanted to do poorly on the 11th rating, knowing that everyone else is going to pick up the slack and get 100s on their ratings, then this one slacker could get a 50. And the store would still average an 85. Okay. All right, so now let's quickly cover, so we looked at how the test can kind of make the familiar unfamiliar and exactly how they'll want you to know averages, mode, median, and range. But now let's look at what may be unfamiliar. So the first topic is standard deviation. Standard deviation is fairly likely to come up on the test. One of these 3 will definitely come up, if not maybe 2 of them. So standard deviation is how far your data deviates from the average. That's kind of in layman's terms. In other words, it's how spread out your data is from where the average is. What do I mean by that? Well, this example has a really high standard deviation. High SD. Why does it have a really high SD? Well, it has a really high standard deviation because you have 5 horse jockeys that are really tiny, and you have 5 basketball players that are much taller than the horse jockeys. Their average height is 178, but if you think about it, 178 is here, but the data points are not even close to the average. So it's not like the data is clustered around the average. So the more spread out the data is from the average, the higher the standard deviation is. The test doesn't get more detailed than that on standard deviation. They just want you to be able to recognize within a data set which one has a higher standard deviation and which one has a lower standard deviation. So in this one, the standard deviation is going to be really high because you have 178, and then the next closest number is 152 and 200. And these numbers really aren't that close to 178. Compared to with, if you had a group of 10 brothers, where the range only goes from 170 to 186, this only has a range of 16. This one has a range of 71. So most of these points, although the average is the same for both of these, they both have an average of 178. In this data set, we have 178 as an average, and then we have another 178, and then 174 and 180, and the numbers don't really deviate that much from this average. They're kind of clustered close. So if this has a high standard deviation, this data set by comparison has a low standard deviation. So standard deviation, it's just kind of how spread out your data is from the average. The more spread out, the higher the standard deviation. Below here are the 4 steps of how to actually calculate it if you're interested. You do not need to know that for the test. It's just there for your own information. And we'll look at a standard deviation problem from the test in a moment. But let's talk about what margin of error is. So margin of error works this way. When we take a survey because we don't have enough time to ask everyone. So if the mayor of London is trying to figure out whether or not we should add more bike lanes, he or she may poll 500 people to figure out, random poll of 500 people just to figure out whether or not they're in favor or against more bike lanes. We don't have enough time to ask the entire population of London, 9 million people. So we're just going to poll 5 million random people. So not 5 million, 500 random people rather than the 9 million. So out of the 500 people we poll, we may get that 73% are in favor of more bike lanes. Well, we don't know that 73% of the entire population would be in favor. We just know that 73% was what we got for the 500 people. So what we do is we calculate a margin of error. And don't worry, you don't need to calculate a margin of error. You just need to know what it represents. So if our margin of error is, let's say, 5%, I'll tell you what this means for the poll. The people who did the poll are telling you, hey, we got 73% in favor on our poll, but we didn't ask everyone, right? We didn't have enough time to ask 9 million people. But we think that if we did ask all 9 million people, it would probably, not definitely, because the only way to definitely know for sure is to ask all 9 million people, but it would probably or likely between 68 and 78% would be in favor. So a margin of error of 5 means that the people who did the poll think that the actual answer for the population that their poll is trying to represent would be within that range of 5% of the 73 that they got. Let's look at a really clever question that tests your knowledge of margin of error. So I'll give you a moment to look at this one. Take a moment to try it out if you want. Otherwise, I'm just going to keep on rolling. So it says, a bottling company sells bottles of water. A random sample of 50 water bottles found that the bottles contained on average 96 liters of water. So we sampled just 50 because we don't have time to sample every bottle. And the estimated margin of error is 0.08 liters at a confidence interval of 95%. This doesn't really come up that often. This just means that they are confident that 95 out of 100 times that they would be right with their margin of error and their average. But we'll kind of ignore that. They're just pretty confident. Which of the following is a reasonable claim to make based on this sample? Okay, so here's what's going on here. We sample 50 bottles. We get 96 liters of water to be the average. We think that if we were to do this 100 times, 95 out of the 100 times, we would likely have an average weight for the bottles between 1.04 liters, or volume, I'm sorry, between 1.04 liters and 88 liters. That's what we think. We think the average most times is likely to be within this range of the margin of error of 0.08. So let me zoom out a little bit. Let's look at the claims. The company always fills its water bottles with less than 1 liter of water. Well, we have no way of knowing that based off of this. What they're saying is that the average was 0.96 for the sample, and we think that the average would likely be within this range. So we don't know what always happens. In the 50 bottles, we very easily could have had one bottle that was, I don't know, let's say 50.50, half a liter, and then another bottle that was like 1.48 liters, right? That's still going to get us an average of about 0.96. So there's no way to know what the company always does, and we can easily have a number above 1 liter and still get an average of 0.96. The company usually fills its water bottles between 0.96 and 1.04 liters of water. B gets a lot of people. So it says usually, so we go, oh, okay, well, this says that the average is likely to be within the range of 0.88 to 1.04. But just because the average is likely to be within that range, that doesn't mean that we don't have the majority of the bottles are either 0.5 or 1.48, and we don't actually fill any bottles within this range, but the average just happens to be within this range because we have a bunch of numbers on each side that would give us that average, almost like a very high standard deviation with an average that's nowhere near where most of the data is. So we don't know this to be true either. The company always, again, always is something we don't know unless we actually sample every bottle. It is plausible, meaning it is likely that on average, the company fills its bottles with 1 or more liters of water. Plausible means possible. It is possible. That is a possibility that because the margin of error exceeds 1 liter, it is possible that on average, the company could fill its water bottles with over 1 liter of water. The margin of error includes above 1 liter, meaning that on our average could be above 1 liter. Okay. Let's talk about the box and whiskers plot, and then we'll hit a few problems real quickly, and then the video will be over. I know this is a long one. So box and whiskers, really simple. The whiskers give you your range. So in this case, we go from about 1100 all the way up to, it looks like someone got maybe a 1600 on that SAT. So the range would be roughly 500, and we get that from the whiskers. The box gives us the 25th to the 75th percentile. So it gives us where the middle 50% of our scores are. Okay, so the lowest 25% of our scores are here, the highest 25% of our scores are here, and the middle 50% are within the box. So that's called the interquartile range. And in this case, the interquartile range is between 1200 and 1480, it looks like. Smack dab in the middle of the box, you have a line, not in the middle of the box, but somewhere in the box, you have a line that represents the median score. So if you have, in this case, let's say 100 scores, if you crossed off 48 on one side and 48 on the other side, scores 49 if you crossed off 49 on one side and 49 on the other, you would be looking at scores kind of 50 and 51, averaging out to this median right here. So anyway, that's always the median. Okay. Let's do 38 and 39 real quickly. So 38. A data set of 27 different numbers has a mean of 33 and a median of 33. A new data set is created by adding 7 to each number in the original set that is greater than the median and subtracting 7 from each number in the original set that is less than the median. Which of the following measures does not have the same value in both the original and the new data set? So I'm not going to write out 27 different numbers, but if you think about it, here's 33. Say we had a 35 on one side and a 31 on the other side. So this data set would have a median of 33, and it would have a mean of 33. If we add 7 to the number above 33, we would have 42. So instead of being 2 away, we'd be 9 away. if we subtract 7, we'd have 24. So instead of being 2 away, we'd be 9 away in this direction. So what happens? Well, these two numbers are still going to average out to 33. And 33 is still going to be smack dab in the middle. It's still going to be the median. So these are going to be unchanged. The sum of the numbers is still going to be the same, right? If I add up these three numbers, it's going to be the same as I add up these three. I don't need to write out 27 numbers to see kind of what's at work here. What does change, though, is the standard deviation, right? What I'm doing is I'm taking numbers that are clustered around my average of 33, and I'm pushing them further away from my average by 7 on each side. So my standard deviation is going to increase. Okay. Let's look at 39. Last one. Okay. I'll zoom in a little bit here. Okay. The results of two random samples of votes for a proposition are shown above. The samples were selected from the same population, and the margins of error were calculated using the same method. Which of the following is the most appropriate reason the margin of error for sample A is greater than the margin of error for sample B? Okay, it's really simple concept, actually. The margin of error for sample A is greater than the margin of error for sample B because sample A has a smaller sample size. How can we think about this? Really simple. If I only ask 10 people whether they're for or against something, and I get that 52% are for, but I've only asked 10 people, that's my sample, I can't feel that confident in what I get. So, because I didn't ask that many people, if this sample of 10 is meant to represent a population of, let's say, 1 million, I really don't know if my 52% is that representative of what would happen if I asked everyone. So if I don't ask that many people, I'm going to have a large margin of error. I'm going to say that I think that the actual number will be far out from what I actually got. But if my sample goes from 10 to, let's say, 10,000, then I can feel a lot more confident that what I got is a lot closer to what would happen if I asked everyone. So the larger your sample gets, the more your margin of error shrinks, right? Your sample size goes up, your margin of error goes down. Anyway, I hope this is helpful. Feel free to read through the worksheet and try out the problems and see how it goes. And any questions you have, you can make sense of it with your tutor. Okay, good luck.